Greetings everyone, it's great to have you back on our channel. Today, we'll be delving into Docker's core, exploring its engine and the technologies that enable it. If you're new to our channel, please hit the subscribe button and turn on notifications to stay updated on our insightful content. Without further ado, let's get started. The Docker engine is a powerful tool that uses kernel-level technology to create containerized environments. These environments are self-contained and isolated from each other. Let's take a closer look at Docker engine's components so we can fully understand how the technology works. The Docker daemon is responsible for managing Docker objects such as images, containers, networks, and volumes. Its role is to execute container-related tasks by taking commands from Docker CLI. REST API. Docker Engine offers a RESTful API to remotely manage containers, images, and networks. Developers can integrate Docker functionality into custom workflows using HTTP requests. Docker CLI. It's acting as an interface between users and Docker engine components. The Docker CLI is a command line tool that enables user-friendly interactions. It helps users build, deploy, and manage containers seamlessly. Containers, similar to virtual machines, allow developers to package code, dependencies, and configurations into a single portable unit. Docker enables developers to run applications across different environments without compatibility issues. If you would like to learn more about this, please check out our latest video on how to get started with Docker. Docker namespaces offer resource isolation, acting as virtualized instances for independent process operation. There are 6 types of namespaces in Docker. The first one, PID namespace. It provides a dedicated space for process IDs, ensuring that container processes remain unaware of any external processes. Network namespace. It isolates the network stack, giving each container its own networking environment. Mount namespace. It provides a distinct file system hierarchy, shielding the container from the host's file system structure. UTS namespace. It allows containers to have their own hostname and domain name independent of the host system. IPC namespace. It safeguards inter-process communication resources, preventing interference between containers. And the last one, user namespace, which ensures the isolation of user and group IDs, allowing secure mapping between container and host identities. Now let's take a closer look at Docker and PID namespaces. When Docker creates containers, it makes sure that each container has its own set of process IDs. This way, the IDs are unique and not shared with other containers or the host system. They do this by using PID namespaces. This helps to keep processes separate and it prevents them from interfering with each other. PID namespaces are a feature that keeps processes running inside a container separate from those running outside of it. What this means? Well, if we had PID of a process in a container A, that means it won't interfere with one in container B or on the host system. Each container has its own space for processes, so the ones in each container only can see the processes that belong to that specific container. Docker uses PID namespaces to create a safe and efficient environment for running processes in containers. PID namespaces create a boundary that prevents unintended interactions and conflicts between processes from different containers. By providing this level of isolation, Docker containers are known for being portable and consistent. Now, let's explore how Docker uses PID namespaces to separate processes in a more practical demonstration. Before proceeding further, please make sure that you have Docker installed in your system. So you can either do that by clicking at the Docker icon at the top bar and see it running, confirming the status is actually installed, or by going to a terminal and typing Docker version, where you'll be able to see the displayed client Docker engine version currently up to this day 2406, or the Docker desktop server version, which is 2407 to this date. Or if you're not entirely sure how to install Docker on your own, you can always refer to our YouTube channel. We do have a step-by-step guide on how to install Docker, going through different editions, features, as well as installing Docker step-by-step, covering specifications and requirements on many different environments, including operating systems. So let's clear up our screen and we'll start by launching a simple container. So once we have all of that confirmed, we will launch a basic container by Docker run -it -name demo container alpine sh command in the end. And we can see that at the moment you can't find the alpine image locally, so it's putting it from the repository itself, and now we can see that we're executed into a container itself. This is because we have the -it flag, which is allowing us to interact with the container itself. We also run the psawks command to list all the processes currently running inside the container. We can check the IDs we currently have listed are 1 and 7 as part of our inspection. So let's take note of those two processes currently running in this specific container. We'll open a new terminal. You can just press Command N on Mac, and we'll start by typing Docker run -it -name demo -container -2, and then using the same alpine image sh. And as you can see here, we'll use psawks again to list all the processes, and we have 1 and 7 running completely isolated in a demo container number 2. And at the same time, we can compare that to the first container. We also have 1 and 7 processes running here, which are completely isolated from one another, which is absolutely a great exercise to understand a little bit better in all of this in detail. Cgroups, which stands for control groups, are an important part of Docker's resource management. Docker uses Cgroups to assign hardware resources to containers and set limits on their usage. This ensures that no single container uses up all the resources, which could impact the whole system's performance. There are 4 types of Cgroups. CPU group governs the distribution of CPU resources, making sure that each container gets a fair share. Memory C group. This regulates the amount of memory that a container can use, stopping any memory hogging. Block IO C group. This controls disk IO to prevent one container from saturating the storage subsystem. And the last one, Network C group, manages the network bandwidth and ensures that each container uses it fairly. Docker's run commands have various options that allow you to fine-tune resource utilization, and we'll share some of the examples now with you. The first one is CPU resource allocation, When using Docker, you can simply limit the amount of CPU and memory resources a container can use by running certain commands. To restrict the CPU usage to a half a core, use the following command, which will be docker run -it and then specifying the CPU limitation to 0.5 using the Alpine image. The second one worth mentioning is the memory resource allocation. You can adjust the value as needed for your own container. Similarly, to limit the memory usage to only, let's say, 512 megabytes, you can do that by using the following command, which will be docker run -it and then specifying memory that is set to 512 megabytes using the Alpine image. Another interesting one is the CPU and memory limitations that are combined together. To apply both CPU and memory limits to the container, you could use docker run -it with CPUs set to 0.5 as well as memory set to 512 megabytes with the usage of Alpine image. This command will combine both CPU and memory limits, ensuring that the container doesn't exceed the specified values for both resources. The fourth one in line is about CPU shares or a relative weight. The command for this is docker run -it and then specifying CPU shares to 256 using the Alpine image. With this command, you can set the container CPU priority compared to other containers on the system, which means the higher the value, the higher the priority is going to be. And the next one is network bandwidth limit. By attaching a container to a specific network, you can control its network bandwidth and interactions with other containers on that network. By using these commands to create a network, you can attach a container to it and assign it as an alias. So first you can do docker network ls to list all the currently existing networks in your environment. And if you'd like to create a new one, you can do that by running docker network create, and let's call it demo -network for the time being. If you run then docker network list command again, you'll be able to see the newly created network in that list. And if you would like to assign it as an alias, you can do that by running docker run -it and then specifying the network, which we just created now. It will be demo -network. And then there's a specific flag called network alias, which can be assigned to my_container using the Alpine image. The next one is restart policies. We will use this command to ensure that a container restarts automatically in case it exits unexpectedly. You can specify different restart policies based on your needs. So if we run docker run -d in a detached mode and setting a flag restart to always using the Alpine image, we'll be able to see that under docker ps, the container we've just created is basically restarting in the background. It's not running any particular service in the container itself, and as the restart policy has been set to always, is continuously attempting to restart container itself. And lastly, to remove all stopped containers, freeing up disk space and resources on your system, use the following command, docker container prune. But please note, this command removes all stopped containers. It is a handy way to keep your environment tidy, especially after running and testing multiple containers, as we did just now. These examples demonstrate how Docker run commands can control various aspects of resource utilizations, such as CPU, memory, network, and so on. You can adjust these commands according to your specific needs and resource requirements. To conclude, namespaces define the scope of containers, whilst Cgroups limit an application to a particular set of resources. Explore the world of Union file systems, which are an essential part of Docker's layered architecture that allows for the quick creation and distribution of container images. By using these file systems, you can deploy applications with ease due to their lightweight and agile nature. In the next demo, we will gain a deeper understanding of how Docker's Union file system work, and you'll see how they improve the speed and efficiency of containers operations. Okay, let's jump straight into the practical demo for this part of the video. And we'll start by checking if there's currently anything running in the background. So let's go back to our terminal and type docker PSA. We can see some containers running there. So let's just do some cleanup. And we'll start by listing all the Docker images at the moment. So we can see we've got a couple of them there. And let's make a new test demo directory. So we can store all our files in there. And let's create a simple Docker file. So we'll do echo from Alpine latest, and then going to Docker file, which will create a new Docker file, as you can see here listed in our terminal. And we'll do docker build -t base image dot, which will be looking at this Docker file. So if we do docker history base underscore image, we'll be able to see one layer that's been added to this image that we've just created now. So let's clear our screen. We can see the Docker file is still there. If we do cat docker file, we only have from Alpine latest image. And let's add echo run apk add no cache curl to our Docker file. As you can see, we've got 2 errors here, which will just add another line. So if we do cat docker file, we can see now it's been added to the top of from Alpine latest. We now have run apk add command. And if we do docker images, we only have at the moment space image that we've just created and the Alpine, which we pulled earlier. So let's create a new image. So docker build -t extended image and dot to look at this Docker file. And if we do docker images, we'll be able to see extended image now being created 4 seconds ago. And if we run docker history extended underscore image, we will also be able to see another layer being added to that image, which is just what we previously created or added to our Docker file. And you can see in the comparison to Docker history of the base image, the first one we created, there's an additional layer added to the second image. And we'll run the last command. So docker run -it extended image /bin sh. So we will going to add another layer directly inside of the container itself. So you can see it did all the fetching that required. We'll now exit the container and we will run this command, which will basically commit the changes, of course, that we've just created now. Made in a container to create a new image layer, basically. So we'll run docker history. We'll call this final image. And if we list docker images, we'll be able to see the final image created 11 seconds ago. And in comparison to the other two, so extended image and the base image where we started from, we can see them all listed in here under Docker images. This demo illustrates the layered harmony of Union file systems in Docker images. Each Docker file instruction adds a new layer. A container based on these images can introduce further changes, each contributing to a new layer. This layered approach facilitates efficient storage, sharing, and versioning of images. Linux containers, powered by namespaces, Cgroups, and Union file systems, offer a powerful tool for developers and operations teams. These technologies collaborate to create a virtualized environment where applications can thrive. As containerization evolves, mastering these technologies becomes crucial for success. That concludes our deep dive into Docker's engine and the technologies shaping containerization. If you found this video insightful, please give it a thumbs up, share it with your fellow developers, and don't forget to subscribe for more content. Thanks for watching and happy coding.